All right, so off to a little bit of a late start, but I don't think I can really talk for fully 15 minutes anyways, so that works out. And forgive me, I am going to read because it's early and I don't want to forget anything. So first of all, thank you everyone for coming. Welcome to DLfM 2021. This is the first time that we have tried an association with the YAML Congress, and we're very grateful for that. We do apologize that it's remote. We hope that next year we can continue this alliance with YAML at an in-person conference. That's sort of yet to be determined. On the bright side, I'm not sure how many of you were at the poster session last night, but using Gather as an interface for a poster session turned out to be a lot of fun. It seemed like it was a success. And it was a lot of interactions happening, people sort of playing pianos and such. And so that was fun to see. There was also very nice attendance. I think at one point there was up to 72 people at one time. And so I'm assuming at least 100 people attended the poster session overall. And speaking of success, I have a few individuals that I need to thank for the mostly smooth organization of the conference. So of course, our general chair, David Lewis, who has been incredibly patient and supportive throughout this whole thing as I figure out what I'm doing, and this continuity between last year's conference and this year's conferences would not have been possible without his help. Our proceedings chair, Nestor Napoles Lopez, who has been extremely devoted with his time. He's been quite the workhorse, actually. So many thanks to Nestor. Our YAML liaison and program officer, Rupert Ridgewell, for helping us to coordinate this with YAML's timetable. And of course, we owe a great deal of thanks to the generous contributions of our sponsors. So for the first time this year, we are able to offer completely free registration for all participants, for all authors as well. And that's really due to the thanks of our sponsors. So specifically, we'd like to thank Georgia Tech, Goldsmiths University, and the Royal Music Association for their contributions. Finally, a great deal of thanks to all of the members of our program committee for their service and for helping to curate an excellent program, which I'm very excited. So we do have a wonderful program lined up today. Our first session, which we will begin shortly, is on novel approaches to audio analysis for classification, comparison, or query. Our second session will be corpora and computational analysis of non-common practice area music. And our third session today, representing chords, intervals, rows, and sets. Then again, please join us tomorrow. We will have a joint session tomorrow afternoon, well, tomorrow afternoon, with YAML. And yes, we hope you will stick around for that. So as a reminder, we will be recording all of the sessions. Some sort of general sort of standards behavior-wise were sent out in emails to all participants. So again, we like to remind you not to do any sort of screen captures or anything like that without permission. For the sessions themselves, for Q&A, you're welcome to use the chat feature in Zoom. We will kind of monitor the chats during the Q&A period. If there are not too many people, you can just sort of unmute yourself. If lots of people are asking questions, we might ask that you use the raise your hand feature. Unless I've forgotten anything, in which case, David, feel free to jump in. I think we can go ahead with our session one. So for that, I am indebted to Kayun Choi, who has volunteered to be our chair for today. And Kayun is an assistant professor in the Department of Information and Library Science and the Data Science program at Indiana University. And if I'm not mistaken, is it an hour earlier there for you, Kayun?
No, it's
the same, same as the East Coast.
8 a.m. Yeah.
Okay, that's good. Yes. We're very grateful for your volunteering to help us out. So I'll pass it over to Kayun, who will lead the session. Thanks.
Yeah, thanks for your introduction. Welcome to our first post-paper session, everyone. So we have 3 presentations. So after a 20-minute presentation, a 10-minute Q&A session will follow. So I will play this gentle alarm 3 minutes before the end of the 20-minute presentation. Okay, the first presentation has 3 authors from the University of York. Mary Emmett has recently completed her PhD on the hunting songs and singing tradition of the Cumbrian Lakeland Felpax. Mary was recently awarded the Jane Moody Scholarship to work on a pilot project, which will be outlined in today's paper session. And Jong Yu-in is a PhD student there with research interests in music generation with deep learning, its evaluation, and exploring various analytic and generative methods based on music theoretic and music cognitive expertise. And Tom Collins is a lecturer/assistant professor in music technology at the University of York, and also heavily involved in the music cooperative Maya Inc. Yeah, Tom studied music at Cambridge, mathematics and statistics at Oxford, and did his PhD on automatic pattern discovery and music generation at the Open University. So I can't wait to hear your presentation, Dr. Emmett. Yeah, the floor is yours.
Great, thanks, Kayun. Okay, I'll just share my screen again. Right, okay, I think we're working. Good. Okay, well, good morning, good afternoon, good evening, depending on where you are, everyone. Thank you for coming to listen to us today. I'm going to co-present this with Tom, I think, so he'll just unmute himself when he needs to talk. And I'll just get started with a quick introduction about the project we've been working on and outline what we're going to talk about for the next 20 minutes. My PhD research focused on the hunting songs of the Cumbrian Lakeland Felpax, which is a folk song tradition that had never been the sole focus of any academic study before. This involved collecting and cataloguing 313 songs, which correspond so far with 147 tunes. When attempting to catalogue the collection for musical analysis, it became clear that there was no existing system that could effectively store and organise the tunes so that they might be A, searched, and B, explored for musically interesting correspondences. Currently, this collection of songs is detailed over various spreadsheets with the lyrics in Word documents and tunes in the music notation software Sibelius. It wasn't possible to create a convenient way of denoting which songs in my collection share tunes with each other, and it was this frustration that led me to have the idea for the archive exploration system that we're going to share with you today. Initially, we've been working on an application which could be integrated into existing library catalogues so that tunes might be made musically searchable. We'll talk to you this afternoon about the feasibility of such a system, outline the prototype we built, review the literature on music search, show you how the archive exploration system we've developed currently works, and finally discuss future work we and others might like to do around this system. Ideally, I'd start off by explaining a little more about my PhD research, which might give you a better idea of the musical material that we've been working with for this project. I'm afraid we don't really have time for that today, but please feel free to ask me about it at the end if you've got any particular questions about it. So instead, let's start by looking at some musical examples. So of the 147 tunes in my entire collection of Lakeland hunting songs, all but 7 are in major keys, the others are in modal keys, and they're all relatively simple tunes. They mostly come from popular song of the last long century or our national hunting song tunes. 80 tunes were used in the development of the system we're presenting today, just because they were already converted to music XML format. So here we go. The transcriptions tend to represent the most common version heard of the many borrowed tunes used by this tradition, but common variants are sometimes included on artist aids, as we can see here in the tune Hark Forward. This is the most commonly used tune within the tradition, and I found 34 songs which most likely correspond with this one tune. Part of what makes this tune so popular and useful is that it can be used in almost a recitative style. A rhythm can be pulled about to fit any given textual underlay. We can see a general or typical version of this tune here, which is the version uploaded to our archive exploration system. There it is there. Because this tune can be rendered in so many different ways, it was important for the search system to be able to return hoc forward as a result if queries contain some of the most common variants, some of which can be seen here. So A at the bottom there, if I click that again, the sort of capital A at the example on the bottom corresponds with the B osseous stave above it. The B example at the bottom corresponds with the C osseous stave at the top. And the bottom example, C, corresponds with bars 3 to 4 of the example at the top, which is using actual rhythm from a text which would be set to it. There are also some tunes with slightly awkward rhythms or where time signatures change partway through. So I was concerned about how a computerized system would cope with these anomalies. An example of this is for the tune 1st of May, which we can see here, which would in the original transcription appear as seen here. The rhythm in this tune should be swung, so the tune actually sounds as is transcribed here, with all the triplet rhythms written out. Neither music notation software nor a music search exploration system would know how to swing the rhythm without being programmed to interpret the textual instructions. But we hoped that the system we created will be robust enough to deal with varied rhythmic inputs of this tune, whether they're swung or not. So at this point, I'm just going to pass over to Tom, if he wants to unmute himself.
Yeah, thanks, Mary. So we'll talk a little bit about music search and what's already out there. It's a topic that's attracted much attention, over many decades. Many people in the room will know of Barlow and Morgenstern's Dictionary of Musical Themes, which is on the screen capture of a page of that is on the next slide. Yeah, we can leave that up, Mary. Since then, there's also been a lot of work, and a bit like the Barlow and Morgenstern, which is shown there in the photo, you can do like a reverse lookup using this dictionary. So if you don't know the name of a tune, but you know how to hum it or write it down in C major, you can go to the back of this dictionary and find what it might be, right? So this top one that goes C B A B C B C, you go to S966 and maybe, I don't know who that's by actually, but Schubert or Stravinsky, it'd be someone starting with S. And that's a very clever idea and has kind of that representation, either using pitch classes or using intervals between pitches, is something that's kind of continued right up to quite recently. Work by Kornstadt on Theme Finder, Typka, who's behind Musipedia, and then Was, I forget the first name, but 2008 is kind of the first time I saw like the folktunefinder.com site emerge. So we kind of were looking at some of these similar tools for finding tunes based on little kind of input note fragments. And of course, we have the SIMSA project as well. All of these kind of need pitch representations or intervals between pitches, or more abstract and clever still by using something like Parsons code, which encodes, up, down, or stay the same movement between adjacent notes. And they have their strengths. I actually think that overall, we probably need a hybrid system that uses that type of approach. And we need something else. And the something else is kind of what's in our paper. So let me allude to that now. The Shazam patent, originally from 2000 by Avery Wang and Julius Smith III, and then some more recent work by Andreas Arzt and colleagues from JKU in Austria, 2012, looks at something else called symbolic fingerprinting or geometric fingerprinting. And the issue with the former approach, where you look at pitch classes or intervals between pitch classes, is that it's very sensitive to interpolated notes or notes that get deleted. So if you query something, but you query a slight variation where that variation includes slightly more notes or fewer notes than what's in the database, then that kind of error between the query and what you have in the database, it kind of propagates a bit, because, you know, where there are, when you're looking at an interval between adjacent notes, that affects several sequences that you've kind of encoded and analyzed in your data set. So the lure to kind of look at our paper is that we've found, you know, from previous work, some examples of systems that are more robust to that type of variation. And fingerprinting or geometric hashing, these are terms that are used to describe that. And that's what we've kind of gone on to develop and build with Mary for this system. But as I say, eventually probably a combination of the two systems working in parallel is the way forward. In terms of representation, we do have the ability to query from audio for this system. And I know we're in a kind of audio analysis section of the conference. But to be frank, what we do is we bolt on an audio transcription algorithm. If someone does query this system with input audio, we basically convert to a symbolic representation and then query in a symbolic musical world. The tunes Mary's presented so far are all monophonic, and indeed across the collection we can assume monophony. But one of the strengths as well of this approach is that it can work very well for polyphonic material too. So I think, Mary, we're ready for the next collection of slides here, where we kind of talk about how the system works. So perhaps a statement of the obvious in the first bullet point here, but a search system should return relevant results quickly. So let's look at relevant and quickly somewhat separate from one another. For a given chunk of music XML data, how do we work with this? How do we encode it? That's what's shown in this kind of second bullet point under the word relevant. In the music notation to the right, you can kind of ignore the triplet instruction for now and just pretend that this is straight eighth notes or quavers. So if you go one more slide, we should have some arrows, I think. Let's just look at this pair of notes. What we do to form a database of something that can be queried is we look at comparisons between pairs of notes that are local to one another in time and pitch. So if two notes are too close together in time, we actually kind of ignore their relationship to one another. Then there's a sweet spot where they're kind of close enough to each other in time, but not too far apart, in which case they're then again ignored in terms of their relation to one another. And similarly for intervallic differences, if two pitches are too close together in interval, they're ignored. Then you enter a sweet spot where there are just kind of close enough in pitch to one another. And then beyond that, again, the relationship of those notes is ignored. And that's kind of just following in the footsteps of how the Shazam patent works and how Arzt et al. Approached a similar problem. They were looking at score following, by the way, in that 2012 paper. And we've kind of moved this over into an archive search world. So looking at the two notes with green arrows underneath them, how do we compare them? We basically compare them as points in a two-dimensional space. So that first G begins just before bar one, beat one. So I've given it an on time or a start time of -1/2, has a MIDI note number of 67. The F sharp with the other green arrow under it, that occurs kind of one beat beyond bar one, beat one. So that's got a start time of 1. If we kind of count start times in crotchet or quarter note beats, counting from 0 for bar 1, beat 1. So that's 1,66, the MIDI note for F sharp there. And then what we want to store is a pitch and a time difference in a kind of compact fashion. So that's what's shown in the quote marks. The -0,1 is a semitone down, you know, the F sharp coming down from the G, and the 1.5 that follows it immediately is just the difference in time between these 2 points. The system that Mary required, we could just look at time differences. If you want to do more complex things like querying at a tempo and the representation in the database is at a different tempo, that's possible, but you need to look at triples of notes instead of pairs of notes. We could get away with looking at pairs of notes in this paper. So we're storing these kind of strings that encode pitch and time differences between local pairs of notes. And then in our Node.js or JavaScript system, for the relatively small data set here, we can actually get away with storing them in one big hash table object. And the clever thing about that, we won't go into details today, but the clever thing about hash table is that the find operation, like determining whether something is in the collection, remains constant and quick, perhaps counterintuitively, even as that collection gets bigger and bigger, even as we throw more tunes into the database here, find is constant and quick. Okay, Mary, we can go on a few slides, and I don't want to talk for too long. So we could maybe just look at the true positive identification here. When someone puts a query into our system, we kind of treat it in the same way as we have the whole collection of tunes. We quickly calculate these so-called hashes. Those are the things within quote marks. And then we look at the times corresponding to matching hashes between the query and the database. And if you go on one more slide, Mary, and we look at a zoomed in plot. So in this plot, you have the pairs of matching times between a query that was found, sorry, a hash for a query that was found in the database, and a true positive in this space looks like an approximately or an exactly diagonal line of points. So if you stare at that 2D scatter plot for long enough, maybe you can convince yourself that there's a approximately diagonal line running from the bottom left to the top right. We can apply a simple transformation to this space, and that's the next slide, please. And what we find is, you know, hopefully a massive maximum value, which shows, you know, it's this piece that this particular query is coming from. On other occasions, you get, you know, multiple close maxima, which then suggests that the query isn't all that distinctive for the corpus that you're querying. So let's go on one more, and we can talk about performance. So this table shows, final column is probably the easiest because it shows the mean time in milliseconds to return results, and it, you know, basically shows what we assert in the paper, which is that it's quick. The top 10 column and the top 3 column, this is, you know, a typical way to evaluate a search system. Ask for a certain set of queries. Is the thing I was looking for in the top 10 results? Harder, you know, question to ask of it, is it in the top 3 results? So we see, if we query with the opening of these tunes and we look at is the thing we're looking at looking for in the top 10 results, we find that yes, it is on 86% of occasions. But if we then limit to the top 3, then actually, you know, nearly half the time it's lower down those results. Again, that implies that, you know, there's issues or topics of distinctivity within this corpus that are interesting to explore. And the second row there, called chorus, rather than just like looking at the beginning of each tune in this collection, Mary annotated some chorus locations, and we just saw if results were similar there or not. I'll hand back over to Mary.
Great, thanks, Tom. So yeah, just a bit of further evaluation. As I mentioned before, one of the things we wanted the system to be able to cope with was common tune variants in both pitch and rhythm. And this was successful in many cases. So if we look at the harp forward tune again and use example A from earlier, we can see the system brings back hark forward as the first result. You can also see here how the system automatically registers queries in the 4/4 time signature, whereas this tune is in 6/8, and yet the system still pulls out the correct result as the top return. We had similar success with a rhythmic variation, which we can see here. When it came to the 1st of May tune that we saw before, when you input the straight rhythm, it returns the intended tune as the first result, but finding a way to input a swung rhythm without it being able to sing it was a challenge. Further development work by Tom to extend the query syntax made it possible to input triplets to a degree, but more work is required to be able to mix crotchet and quaver triplets within the same beat. Nonetheless, we were able to get the start times and pitches in the correct locations. And even as durations are not as they would be in a performance, note durations themselves aren't taken into account by the search system anyway. However, this triplet query didn't return 1st of May within the top 10 results, which again we'll return to presently. So just some conclusions. Today we're showing you the prototype archive exploration system we built, though not properly, but we can do in questions if you'd like us to, outline the ways in which we hoped it would be able to work, and then discuss whether this has been successful or not. Having come to this project with no prior knowledge of coding or digital musicology, this has been an eye-opening experience for me, and I'm really pleased with the work we've managed to produce in this pilot project. So far, the system works really well when we input queries that are an exact match for my original transcriptions, even if we use a different musical key. However, and perhaps not surprisingly, more work is needed to return correct results when tune variants are used in a given query, as often these are less similar to the original transcriptions than another extant tune. And then just finally, delving into some of those problems a little further just before we finish. The 1st of May triplet query example failed to return this song because in terms of rhythmic spacing, the straight to triplet alteration disrupt the musical skeleton of the tune. A solution to this would be to reduce the level of temporal similarity required for a match, but this would likely lead to an increase in false positive results in other scenarios. This is an example of where the pitch sequential approach of systems such as Folk Tune Finder is superior to the geometric hashing approach that we've used, because the pitches remain the same, but rhythms are quite apart. That said, this example is the only case where geometric hashing fails when searching this collection of songs. So overall, for this application of music search, we would suggest geometric hashing is at least equivalent to the pitch sequential approach. Further work and more rigorous evaluation is needed to settle this matter definitively, and probably a hybrid system, as Tom's already mentioned, would probably be preferable overall. Distinctiveness is a topic that's come up a lot during this work. We're still investigating cases of failure for the results presented in the quantitative evaluation, and some may be due to what we're calling an anacrusis bug, as it appears that all but 2 of the failure songs start on an upbeat. But in other cases, not retrieving the intended song within the top 3 or 10 results comes down to distinctiveness, or a lack thereof of the query and or material in each song. As I hope to go on to exploring in my postdoctoral work, there is a lot of overlap between melodic motifs in these songs. So it's to be expected that for a given opening query, there might be 3 or even 10 moments from other songs that match equally well. So the target result may be further down the list. A wealth of literature from music psychology could be brought to bear here, and acknowledging and deciding if or how to model within future research phenomena such as humans being biased in various ways in terms of music memory formation, whereas a computational search and exploration system such as that we've developed here is much more democratic. So thank you for listening, and we'd be happy to take any questions you may now have.
Yeah, thank you. Yeah, please raise your hand if you have any questions. Anyone? Okay, then I'd like to ask one question. So your search algorithm is very flexible in finding variants of a music excerpt, right? And I think that such flexibility can benefit other tasks, MIR tasks, like cover song detection or plagiarism detection, like that. How do you think about that?
Shall I start, Mary? You come in if you've got any additional thoughts. Yes, I think it's a good observation, Kai, and I think that the geometric approach, and in particular, fingerprints formed from the geometric representation, could assist in other MIR tasks if they haven't been applied to date. And as I see it, it's the score following work of Andreas Arzt. And then this, where maybe gradually it's seeping in. Perhaps other people know of other examples. I know I saw Daryl. I saw the name Conklin in the room earlier. I know that a long time ago he was looking at representations of viewpoints where you kind of only look at a note on a downbeat and kind of form a more abstract representation of a melodic skeleton. So it's not exactly the same as that, but I guess what I'm saying is that there've been these clever representations around for a while and variations on them, but I think it perhaps takes a while for some of our more audio-focused MIR colleagues to realize their utility.
Thank you. Okay, I think Chris has a question.
Hi there, can you hear me?
Yes.
Yeah, okay, thanks. That was a really fascinating presentation. I've done something similar on the ABC notation website, and I'd love to chat with you a bit more extended. But my question was, have you thought about encoding the bar lines into the query and into the database? Because I found when I did that, it made a big difference in the accuracy, assuming that people know where to put them.
Yeah, Mary, do you want to say something about that with respect to the musical material here, and then I can perhaps ponder from a technical angle as well?
Yeah, I think I can see how that would be really useful, but I think the problem is the point you make, assuming people know where they go, because part of producing the system is, for want of a better term, we're trying to make it as idiot-proof as possible. So we're kind of assuming that people using this system will probably have no, or it should be able to be used by someone with no musical knowledge at all. The people involved in this tradition wouldn't describe themselves as musical in any way. And I think kind of them needing to have some musical knowledge to be able to use the system would be quite off-putting. So yeah, it's certainly something that would be interesting to look at in the future with this. I'm waffling. I'll let Tom take over and maybe say anything else if you want to add on anything.
Well, I think that's a good point, Mary. As we were kind of underway with this project, we wanted the system to work, and then we bolted on a way that you could enter music notation with a reduced syntax, and then Mary kept reminding us, well, it's not that's not the users I have in mind here, people who are willing to sit down and get the music notation for this right. I want them to be able to play something in or sing something in. So we co-opted some of the Magenta onsets and frames transcription code that's available in JavaScript, and built a audio front end that works well for if you're playing an in-tune piano but still singing at it. You get quite bad transcription onto staff notation. But to go back to the comment about ABC, yeah, thank you for the ABC site. That's a wonderful resource. And I guess I'd echo Mary's point about, it's only useful if the person querying knows where the bar line is. But I completely agree that if they do and they want something that is located in a particular point in the bar, that's really going to help with the apparent performance of the system. On the other side of that, I remember participating in the artificial intelligence for music generation competition organized by Bob Sturm last year, which used ABC notation. And I was surprised to hear repetition in some of these deep learning algorithms for music generation, because they don't have as long an attention span as people often talk about in the titles of papers. That's what I said to Bob, where's this knowledge of repetitive structure come from? He said, oh, well, they've learned the repeat signal in the ABC notation. So I thought it was quite funny, because they hadn't actually learned about musical structure, but they'd learned a symbol, and that symbol occurred and it caused a repetition. Yeah.
Okay. I mean, I don't actually have a melodic search on my site, but I do use the bar lines for finding variants. So if you find a tune on the site by the title, you can then see all the variants on that page. And I mean, I found the bar lines made a big difference there, obviously. Once you've got a tune, the search engine knows where the bar lines are from that tune, and then it can then apply that to find variants of that tune.
Yeah.
Anyway, fascinating talk. Thanks very much.
Yeah, I think Jeff has a question, and it will be our last question because of the time limitation. Yeah.
Yeah, thanks very much. If there isn't time to answer this question, actually, I'm happy to talk about it offline. So there's no rush. But I was just really interested in, first of all, thanks for the talk. It was really interesting, and seems to be quite similar in some ways to what I'm looking at. So that's really cool. I'm basically alignment of sources, of audio sources with different tempi, or even a single source with sort of varying tempo throughout the source, is something that I've been sort of tackling. And I'd be really interested to know more about how you think you might approach that. You mentioned using triples, and yeah, so I don't think we have time to discuss it now, but maybe Tom or Mary, if you wanted to get in touch later, I'd really be interested in talking about that and finding out more about, you know, what your thoughts are on it and how you've kind of tackled it so far with tempo invariant sources.
Sure. Yes, we can talk more offline. I think the quick answer is that you kind of, if you've got a triple of notes, you compare the first note and the second note in terms of their time difference, the second note and the third note in terms of their time difference, and you form a ratio. Could be like the first time difference over the second one, or the other way around, as long as you do it the same way throughout your analysis, and that can help with a scale factor. The query kind of has to be at one, you know, we assume the query is short, and therefore the scale factor is relatively constant over the query, and then that should still work even in the database if there are lots of tempo changes.
Cool, thanks.
Thank you so much for the talk, Tom and Mary, and all the great questions and answers. I think it's time to move on to the second presentation. Just let me open the email, Nico. I'm really sorry. Should open. I just received an email about the introduction, and let me pull off the email. Okay. Yeah, our second presenter is Nicolas Dialeman Arango. And Nico is a sound artist, musicologist, and researcher. So he is currently a PhD candidate at the Hesse-Plattner Institute for Digital Engineering at the University of Potsdam, Germany. The results of this paper are based on his master's project for the Sound Studies and Sonic Arts program at the University of the Arts in Berlin. Yeah, yeah. Nico, would you please take the floor?
Yeah, thank you, Kayun. Yeah, so I will first share my screen. Okay. And then I will do this. Okay, does that look good?
Yes.
Okay, then I will start. So yeah. Okay, so my paper is called Archiving the Sonic Ephemeral towards a classification of sound installation documentations through spatial audio features. And yeah, this is a chapter of my master thesis, and yeah, I'll go. So this paper proposes the application of audio feature extraction for the classification of sonic documentations of the works presented during the Singur Hörgalerie project from 1996 to 2014. More specifically, I used the stereo panning spectrum features to discern some of the relationship between the artworks based on the spatial characteristics of said documentations. The first part of this paper addresses the theoretical concerns that emerge from documenting a form of art that champions ephemerality as one of its core characteristics. Audio recordings force sound installations into an ontological reality and effectively positions them in the musical realm, thus subjecting them to a one-dimensional interpretation. An approach to overcome this paradox is built upon Kerstin Glandian's proposal to analyze sound art. The second part describes the technical processes of examining the Singua recordings through the proposed algorithm. The results present a novel form of approaching sonic documentation by analyzing spatial relations between audio sources and how to incorporate them in additional documentary and archival material. Considering the challenges of the documentation practices in sound art installations, open up the discussion of archiving ephemeral sonic events and other site-specific nuances that are becoming more and more present in contemporary music. This modest proposal for analyzing spatial features of documentations could potentially be applied to more traditional musical settings, for example, Luigi Nono's Late Over or some multi-channel setups. Likewise, this also serves as a forum to question and challenge the ways in which documentation practices are preconceived and how could music information retrieval broaden its applications into artistic practice. Now, so what is sound installation? So here I want to talk about like some small nuances in the definitions of terms, and so as Andreas Engstorm and Asius Sterna point out, the term Klangkunst has a much narrower designation than the English term sound art. The works in Klangkunst usually bring attention to the acoustic, spatial, and architectonic characteristics of sound. They create a connection between auditive and visual elements and between time-based and space-based arts, while avoiding any association with performance practices. For Helga de la Motte Haba, the need of addressing the site specificity as a structural part of this practice positions Klangkunst within the context of land art, which, quote, turns places into a subject of discussion in their own right, unquote. Many works of Klangkunst go beyond the articulation of space and sound and establish multidimensional forms of perception situated between the sonic and the visual. This adds a layer of complexity to the documentation of such artworks. Not only media needs to be included in the documentation process, but also the visual material and its interaction within the overall experience of the piece. This one-dimensional perspective captured by a pair of microphones obliterates the core elements of Klangkunst works, namely acoustic spatial awareness, multimorph forms of perception, and non-linearity. Karsten Glinden's proposal to analyze sound art recognizes the need to take into account the non-sounding components of artwork. This includes the visual elements, as well as the spatial and the multisensorial experience. Audio recordings are therefore less than ideal tools to analyze sound art, given that they cannot grab the totality of three-dimensionality. The linear monosensory modes of perception are forced by the sound recording challenge the nature of the open work. Although audio recordings are indeed an ideal source for computational analysis, they are often just a representation of the musical work. Thus, the analysis of sound art poses more than an aesthetical question, an ontological one. What is a piece of sound art and how can we identify it? Umberto Eco notes that every work of art is indeed open to a virtually unlimited range of possible readings, but the open work as such is to be seen as the actualization of a series of consequences whose premises are firmly rooted in the original data provided by the author. Unquote. What situates sound installations as open works is specifically the auditory design of the pieces, that is, the data provided by the author, and not necessarily the overall visual and spatial component that complements it. Moreover, it is the sonic element of the installation what makes it sound art, right? And not just an installation with some other sonic component like in media art. In musical practices, an open work is an invitation to the performer to create the work together with the author. In sound installations, the perceiver becomes the performer who creates the work together with the artist. Even though the totality of a sound installation cannot be grasped by an audio recording or by a single witness, every subjective perception of a piece has the potential to create an equally valid interpretation. Since the work is perceived differently by each subject, it is created while it is being listened and perceived. In that sense, a computational analysis of the sonic components of an installation is as valid as any form of analysis, since it is the act of the listening machine that actualizes the piece. Yeah. Okay, so contrary to the practices of electroacoustic music, these audio examples are not the end result of the artwork, nor do they function as scores for reinstallation, reinterpretation, or even though often they run the risk to be mistaken for the artwork itself. In that sense, the documentarian, be it the artist or the audio engineer, creates a sonic impression of the work, an own interpretation of an open work that is as valid as multiple interpretations and constructions that can arise from documentary practices. These audio documentations can already tell us a lot about the installation themselves and are subject anyways to be analyzed, archived, and cataloged according to their audio features. The sonic material found in the pieces of Klangkunst often challenges traditional musical associations and tend to focus on sonic elements that explore spectral and semantic aspects of non-musical sonic material, such as noise, soundscapes, and speech. Klangkunst avoids being scrutinized by the pre-established structures developed for musical analysis. Although some of the data acquired through spectral analysis, such as pitches or readings, could be significant in the analysis of some sound installations. This is often irrelevant in the complete framework of the artwork. Hence, the ordinary tools provided by music information retrieval are not adequate to obtain relevant data for sonic characteristics of the documentations. What I propose is a careful analysis of the spatial components of the sound that has the potential to reveal overlooked details about site-specific sound. This is the Singuo project, which play a significant role in the establishment of Klangkunst as a genre. It is the application of the theoretical framework that evolved from the mid and late 20th century in the musicological discourse of experimental music. The first part of Singuo project was developed between 1996 and 2006 in the parochial Kirche, that's the one on the left, and the second part was took place from 2007 to 2014 in the Wasserturm and Wasserspeicher, so all water reservoirs in Berlin. That's just for some context. Okay, now my approach explores the use of stereo panning spectrum features as described by Chatsenakis in 2007. It is an audio feature that calculates the general balance of a stereo signal per frequency bands. Its main purpose is to analyze the production methods of a stereo image on a stereo track. In their words, quote, "The proposed features can be viewed as a first attempt to capture the extra musical information related to the production process through music information retrieval." In short, stereo panning spectrum compares the left and the right channel of a stereo signal and looks at the difference in the amplitude per segment of time by a given window size per frequency bin. It reveals the ways in which panning characteristics of a given recording behave over time and in each frequency range. Stereo panning spectrum is also helpful to discover mono-duplicated signals and is also very sensitive to noise information. That is, stereo pairs recordings often leak information from one channel to the other, while precise panning positioning is only possible in studio productions. This is shown in the images. This is the image in the right is actually the result of analysis of a song by Kanye West, which uses a LFO to control the panning from left to right, and you can see very clearly that is a sinus wave. Yeah. Yeah, the use of stereo panning spectrum features is convenient for the analysis of sound art recordings for various reasons. First, it is presented as an analysis of production techniques rather than acoustic analysis. Thus, we can analyze how the documentations were recorded instead of an analysis of what is recorded. Second, the analysis of a panning spectrum reveals changes over time in the stereo images. Clear distinction between left and right often indicates several audio sources, multi-channel installations, or recordings. Whereas pieces with regular, that is, noisy distribution through the stereo image indicates installations that interact directly with the architectural characteristics of space and its perceptual properties, that is, more immersive. Third, because the difference of energy per window beam, pictures can reveal more information about the sound sources of the installation, unlike some other features like phase correlation measurements. And for example, the movement in the low frequency bands often indicates the use of subwoofers or the presence of subharmonic beatings, as is shown in the image. From there, 16 vector of stereo panning spectrum features was extracted from each of the 112 audio samples of the Singuo tracks found in the DVDs of the catalogs. The resulting vector was averaged, representing the overall amount of movement in the stereo image for each track. By sorting the files according to this number, the results are already quite satisfactory. You can see it on the table. The pieces with the highest values, for example, Jutta Ravenna's Traum und Wahrheit on the left or Christina Kubisch's 33 Felder in the right, are composed by amount of small single sources, so all the speakers, and there in the left there are a lot of electromechanical circuits. Whereas the pieces with the lowest SPF average are usually like either monophonic recordings or have a stable image, such as Mickey Joey's Innerest, which is on the left, or Johannes Oventur and Martin Supper's Stilgung, which is in the right. These pieces are the ones that engage mostly with the architectonical characteristics of the space, and this is the image of how they look in this sort of like spectrogram, and you can see that white means more noisy and stable, whereas on the left you can see very clear distinctions between left and right, which is red and blue, of course. Okay, almost there. Creating a first approach to analyze and classify the documentation of sound installations is a manifold exercise. First, the goal is to demystify the aura behind the sound installations and challenge the assumptions about sound art. The fact that these sonic documentations exist make them already available to scrutinize and analyze. Furthermore, getting to know the sonic characteristics of these installations through the lenses of audio analysis opens up the opportunity for new discussions regarding indexing, generating classification, and archival processes. Once we're able to clearly recognize these characteristics on the audio documentation of a sound art installation, further questions can be asked about the intention and experiences of the piece. If the piece is immersive, that is noisy, how is this actually achieved sonically? What kind of spatial perceptions are in play in such pieces? If the piece has a more dynamic use of space, where are the sound sources? How many are they? What are the sonic characteristics? How could they affect our perception of space? And ultimately, how do we as listeners and creators of a piece engage with the data given by the author? Some of these questions could be asked when considering the practical details of the documentation processes themselves. what kind of recording techniques suit better the documentation of this or that sound installation. In that sense, sound art documentation as an artistic practice gains its own aesthetic ground, mainly by weighting what is left behind and what is included. And yeah, so I have presented this somewhat unusual approach to the classification of a somewhat unusual form of sonic documentation. The idea was developed from my own curiosity on listening machines as tools for creativity and their application in an artistic setup. Still deemed this discussion important because, as Folcastrevel has claimed, there is a new generation of sound artists that appear to be always reinventing the wheel, leaving us with the sensation that the same ideas have been used to exhaustion. Arguably, one of the reasons for this is the lack of tools for engagement with the sonic archive. My proposal then is to find new materials by reconsidering the ideas of the past and not only relying on subjective descriptions of the pieces or technical and acoustical analysis, but also including machines as agents of creativity. Novel applications of acoustic analysis could be relevant to further analyze and classify sound installations. Music information retrieval is mostly implemented by extracting meaningful traditional music features, while something like computational auditory scene analysis relies on acoustic features of speech and soundscapes that are not really suitable for sound installations. Other forms of acoustic analysis could be implemented in order to better understand the sonic material of sound art. In general, computational analysis and classification of audio files has an enormous potential as a creative tool for sound art installation that has yet to be explored more extensively. Yeah, thank you.
Thank you. Yeah, if you have any questions, just raise your hand. Yeah. Thank you for the awesome presentation. And yeah, there are so many questions about classifying such sound artworks and how to archive them, right? So my question is, so you use sound and you use the stereo panning spectrum features. Actually, the final result of the feature has 16-dimensional vector, right? And you average the vector to get the index to classify the artworks, right?
Yeah. Mm-hmm.
So how about, and I thought that each dimension of the 16 dimensional vector probably has some meaning, and I'm not quite sure the averaging, how averaging actually affect, influence the change of meaning. And have you thought about just use the 16-dimensional vector as an input to a clustering algorithm, so you can actually find the clusters?
Yes. So basically what I did, I'm just following the paper by Tsatsanakis and all, and he describes the vector very well. So I thought like I will leave that to you, because I mean they explain it pretty well, and that's a little bit beyond my expertise. But what I was thinking is like, I thought the next step would be to feed these vectors and these matrices and these results as they are to recommendation systems, or like that kind of more advanced algorithms that are also described in the paper by Tsatsanakis. So that will be the next step for me. and that's something that I'm still really looking forward to have the time to do some more research. Yeah.
Yeah, I think you can find some clusters.
Yeah, for sure.
Yeah. And anyone? Okay, then I have one more question. Okay, so it seems that the features that you are going to use captures the information about some production processes, right?
Yeah.
And as mics play a very significant role in sound production, so I'm curious whether you actually have more information about mic settings. So you have a data and DVD, and do you think it's important to report more information about mic settings along with the feature values?
Yes and no. Like the first recordings of these sound installations, they were usually either made by the artists themselves or made by different audio engineers. The second part, they were done by only one engineer, Timur Klosche, and he and in that book, in the second book of the documentation, there is a map where they place, like, this is the tower, and they put the where the microphones were placed. But I talked with Timur, and he told me that most of the stuff was recorded with stereo pair, and what I found interesting is that in those examples there was also, for example, there was one installation that was just a telephone in the middle of the place, and if you pick up the telephone, it was one of those telephones like this. You could actually listen to some pre-composed piece, and when I put it through the algorithms, it was like clear that was a studio production, right? Yeah, so in that sense, that is one of the things that you can find out with these stereo features. Yeah.
Thank you. And is there anyone who has a question? Oh, okay. Who raised your hand? Oh, okay, Claire.
I had two questions. One is a bit more sort of philosophical, but the first question actually has to do with, it's sort of related to what Kayun was just saying, but a lot of sound installations that I've seen feature more like of these arrays of speakers and surround sound and things like that. And so I'm just curious, first of all, kind of how much of that kind of movement is being captured with the panning, which is really this sort of just one-dimensional thing. And if, have you thought about, is there any way that you might be able to kind of expand this idea of the space or the movement with some other feature or combinations of features?
Yes. So I think for my goals and for a first approach to this problem, the stereo documentations did a pretty good job. Of course, because only until recently the availability of things like Ambisonics microphones or like other forms of like real 3D spatial forms of recording have been like made consumer available. That's still something that a lot of artists and documentarians are working with, but just recently. And once you have that, there has been a couple of papers. I found a couple of papers that talk about multi-channel and ambisonics analysis of sound for these multi-channel setups that could be, of course, more comprehensive. The problem that I found while doing this research is that I wouldn't find a corpus big enough of these documentations that would give me any information, relevant information. Actually, the reason why I choose this corpus of documentations was basically because it was already done for me. So that sort of like saved me some time to like actually do the whole processes instead of curating the thing myself, which would have been like super time consuming, and yeah, that was not the goal.
Yeah, I think there's many people here that can sympathize with that. The other question was slightly more philosophical in the sense that you mentioned at one point things like, the idea of the recording just being sort of like one instance of the work, or sort of the listening machine as sort of like, an agent or sort of another possible interpretation, and that each one is different and unique. And I would kind of argue that that's really true of almost all forms of music, but perhaps you'd like to say something about why that's maybe especially kind of important in this case, or it's kind of an additional hurdle for the music that you're studying in particular.
Yeah. Yes, I mean, I think you're right in the first part. Like the other thing is that because this form of art is trying to step out of the tradition of music, there is a lot of emphasis on the site specificity and the immersion that you get through these sound installations. That is not only that you listen to the sound and then you get like an immediate idea of what the piece is, but rather that you experience it, that you're immersed in sound, that you engage with sound not only with your ears but also with your eyes and with your whole body, right? There is a little bit more holistic approach, so to say, and this is just me being like a little bit on the safe side, like making these arguments, because when I started to do this research, I found a lot of resistance. I'm saying like, well, yeah, but those documentations, they were made just like to show something, but you cannot really get anything from them, and you cannot use them like that because the artist will be like really upset and they want you to be in the space, and these things are ephemeral. And I also felt like there was a lot of resistance that was mostly ideological to some degree. In the philosophical side, the other part of my master's project deals with that, and I'm thinking about the machine listening not as an algorithm, but as a transhuman form of listening that enhances our sense of listening. And I talk about the ways in which listening machines relate to space and to resonance and to reverberation, space and self-identification. So there is a lot of also like philosophical background that I took into consideration precisely to contrast this ideological resistance that I was finding while doing this research. So I'll be happy to share some of that.
Sure. Yeah, I think you will find sort of a lot of like-minded individuals in certain sort of academic circles. For instance, I was at a conference a couple of years ago at Berkeley, and a lot of the sort of things that you're saying, Carmine Cella was there, so sort of has similar these ideas of how can we analyze this, how can we sort of archive this, how can we preserve this, but also kind of pay homage to the people who've made it and respect how they want the materials to be used and so on. So yeah, it's an interesting topic. Yeah. Thank you very much for your presentation.
Yeah, thank you very much. Yeah, and I think it's time to move on to our next presentation. Okay, our last presenter of this session is Jeff Miller. Jeff Miller is a professional musician and PhD student at Queen Mary University of London's Center for Digital Music, in collaboration with the Research and Development Division of the BBC. His research involves geometric modeling of chord sequences for content-driven music recommendation and discovery systems. Yeah, he wants to help an algorithm suggest music like your best friend would. Okay, the floor is yours, Jeff.
Okay, thanks very much. Let me just get my screen sharing going, and hopefully it will work. I'm always a little bit suspicious. Right, can everyone see my screen okay? I will assume so.
Yeah.
Okay, great. Okay, well, thanks very much for giving me the opportunity to present this as a bit of conceptual work that we've been doing over the last year or so. And basically, it's about trying to use graph theory to compare harmonic sequences of content in music. So in the sense that rather than using statistical measures where we're just looking for the total number of particular types of chords in a piece and kind of saying, well, this piece is, this recording is 35% C major and 42% F sharp minor, which is the way a lot of the content-driven chord stuff really works. We're actually trying to find some kind of sort of semantically meaningful patterns within there in the way that a human would hear them. Okay, so to start off with, the thing that this is all about is called the chord sequence graph, and I'm going to start by showing you a picture of one so that there's some point of reference for the rest of the presentation. And don't worry about the detail of this too much, so don't get caught up on trying to look at it, particularly because some of the elements are quite small. But this is a chord sequence graph, and basically it's just a way of depicting chord sequences in a graphical notation that shows shows the different sequences in the way that we move through the piece in time. So basically, time goes from left to right, roughly. It's not hard aligned, but it's basically as you go from left to the right, that follows the passage of time. And you'll notice that some of the nodes are bigger and some of them are smaller. Some of the little arrows are bigger and some are smaller. And the bigger something is, the more important it is, and the smaller it is, the less important. So as we're going through the presentation, don't worry about the fact that there's a lot of stuff on there, a lot of information, and that a lot of it's hard to read, because that's actually kind of the point. The harder it is to read, the less you need to worry about it. So, right. So I just want to start by explaining what a chord sequence graph is, and perhaps as importantly, what it isn't. So a chord sequence graph is an association network that records chord sequences and transitions. So it's similar to, when you read papers about social networks like Facebook or Twitter, often they're association network diagrams. Also, it's used for things like biological interaction networks, food chains. It's about finding the way that things interact with each other. So it's the big picture kind of view, and hopefully using these association networks, they sort of reveal things about a system that you might not notice if you're just looking at the specific instances of data that are within there. So it can be used to analyze a single piece of music, or it can be used to analyze a collection, depending on how it's implemented. And it reveals recurrent patterns of chords, and thus the underlying harmonic structures of the source material. Excuse me. Now, equally important is what chord sequence graphs aren't. So just to avoid any confusion, they're not coordinate graphs. They're not like a Cartesian graph with an XY plane. It's nothing like that. They're not in any way trying to show qualitative depictions of things in space. So they're not harmonic networks like Aton nets. It's not a voice leading network that shows you the distance between two chords by the way the pitch classes change. And they're not perceptual. They're not, so the locations of the blobs at the moment anyway are kind of irrelevant in terms of the distance and closeness to each other. That's not an indication of how similar or dissimilar various chord events will sound. A quick note about mapping source data. Now, the chord sequence graph will work with audio or symbolic data in theory. Our study is focused so far on audio source data, but as I was working on it, it became obvious that that it will work with symbolic data. And in fact, The way it's worked is we've used algorithms to extract chord sequences from audio autonomously, and those are then represented as symbolic data. So, basically, in theory, it can be used for either source domain. A few considerations and constraints just before diving in. One of the big questions with this is what I call the chord lexicon, defining that, and that's basically deciding what's the chord description space. Are we going to limit ourselves to major, minor, dominant seventh chords and nothing else, which is a really easy way to get positive results? Or are we going to look at, all 4,000 odd permutations of all the different pitch classes and keys and things and try and figure out, that level of detail? And of course, both of those are not really that useful. So we have to find a middle ground to focus on. And so we've focused on somewhere about probably 40 or 50 chords. So basically majors, minors, diminished, augmented chords, extensions into the sevenths for all of those, and also major and minor sixth chords. I think that's all of them. The next question is about harmonic granularity, and that's how big of a piece of music are we looking at when we're describing this stuff? So are we describing every 8 bars? Are we describing an entire piece boiled into one metric, or are we actually looking at every individual 30-second note and trying to say what's the chord right there? I'll talk more about how we handled that in a minute. And the third and quite important bit of information is that voicings are not considered in this. So basically a big part of it is that it's supposed to be resilient to noise in the signals, so discrepancies in the translations of the chords or the representations of the chords. And so roots are not considered. The cardinality of the chord isn't considered. So if you have 2 C major chords and one has 15 Gs and the other one has 3 Gs, as long as they've both been identified as C major, that's all that matters. And the inversions are not considered. Right, so, excuse me, gone the wrong way. Diving in. Now, let's look at building a chord sequence graph. So to start off with, we start off with a simple chord sequence, which I've defined here, F to A dominant 7 to D minor 7, etc. The slashes, if you're not a musician, those are basically musical shorthand for musicians who are reading chord sheets to show that you've got 4 beats of F, 4 beats of A7, 2 beats of D minor 7, etc. Now, we do use that the initial length of the chords for alignment purposes at the beginning of this, but once the stuff goes into the graph, the actual durations of the chords is irrelevant and it's not represented in the graph. So we take this first initial chord sequence and we convert it into a one-dimensional directed graph. So if you're not familiar with these, if you look at these white circles, you'll see that each white circle has a chord in it and that there's a little arrow going from each circle to the following circle. And so it's quite self-evident. This is an F major chord, which then is followed by an A7, which is followed by a D minor 7. So the direction of the arrows is significant. And if you're not familiar with graph theory, that is called the directed graph. There are some graphs where there are no arrows and they're sort of direction, the direction there can go either way. And finally, I'll explain this more in a few minutes, but you can associate a weight with each edge, or you can give a weight to each edge and to each node, which kind of determines its importance or clarifies its importance within the graph. And initially, we set all the edge and node weights to 1. Now, if we want to build a sequence, a graph, we have to add at least one other sequence. So the top line is the one that we've just looked at in the previous slide. The following line, the second one, is the new sequence that we're going to be adding to that. So there's a few steps that we have to go through. The first one is that we have to align these in time to try and figure out how do they line up, because that's actually a non-trivial question. In fact, it's a lot more non-trivial than I suspected it was when I started working on this, but that's probably not surprising now looking back. So basically what that means is if I've got an A7 chord in each one of these sequences, does it represent the same musical event within the form of that piece of music? So the way that we've done that is we basically line the sequences up, and And then we implement something called a fractional beat unit, which I haven't really detailed in this presentation because it's a bit more complex, but essentially it figures out a proportional length of the chord relative to the tempo of that particular recording. And then we use that to align them all on a grid, and then we can determine whether those events overlap, and if they overlap, then they're considered to be the same source event. So we line them up. We identify chords that are in both sequences. So as you can see here, there are some little blue arrows connecting these A7s, D minor 7, and the B flat minor 6. Those are all aligned. So when that happens, what you do is you keep one of those in the graph, and then you add the weights of the existing graph with the new sequence. So in this case, the weight of that A7 is 1. The weight of this A7 is 1. So in the graph, we'll have one A7 circle, but it will now have a weight of 2. And likewise, because there's an arrow that goes from the A7 to the D minor 7, the D minor 7 occurs twice. It also has a weight of 2. But significantly, there's a transition from A7 to D minor 7 twice. And so that weight of that one is 1, and the weight of that one is 1. So in the resulting graph, the edge also has a weight of 2. Finally, if you can't find a chord in the existing graph, such as this F6, this is a new one at the beginning, or there's an A minor later on, then you create a new node, you create the edges as necessary, and you set the weights of those to 1. Right, so the top line is just the second graph that we showed, second sequence, and the result of those two sequences when added together is this chord sequence graph on the bottom pane of this diagram. So you can see we've got the F and the F6, they're both going to an A7, both going to D minor 7, and then it diverges, and then it comes together again at the end into a B flat minor 6. In the lower right hand corner, there is a key that shows the node weights, and each of the arrows has a little number, which is its weight, and also the arrows get a bit thicker, and the color starts to change. And basically, the gist of this is that the bigger the circles are, the more important that chord is, because it's occurred more times in the source material that's contributed to the graph. And the same thing applies to the edges. So now we're going to add a third sequence. You'll see this one's a little bit more complicated. We've got a couple of new chords before the A7 this time, F major 7, D minor 7. So we've created some new nodes for those, you'll see here. Everything's got a weight of 1. Now, we've got another A7, another transition to another D7. So if you look in the lower right-hand corner, you'll see that the node weights have now increased for those events to 3, and they're even bigger, and they're colored even more prominently. Likewise, towards the end, you'll see that we've got still 2 B-flat 6s and 2 B-flat minor 6s. So you can see that those chords have occurred more often than a single time, but not as often as these larger, darker circles. Now, I'm just going to take a few minutes to walk through 3 examples of chord sequence graphs that we put together as an experiment to just see if it actually works. So a quick word about the sources. So the source material, we decided to use Georgia on My Mind, which is, you'll probably know, is a well-known jazz standard tune. It's got a really distinctive and easily recognizable chord progression. We limited ourselves to the first 4 bars of the tune itself because we needed to keep the graph size manageable just in terms of looking at it and analyzing it. But in theory, you could make these graphs longer. We haven't studied the complexity of doing that yet, but obviously that would make the problem more complex. So it's the first 4 bars of the tune. And so we looked at 25 recordings of different styles, different instrumentations, blah, 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 and came down to 2 source recordings we decided to work with, an instrumental traditional jazz band recording and a version by country singer Willie Nelson with his country band. And these were chosen because they were highly contrasting in terms of the tempo, the genre, style, the lineup of the groups, and the arrangements that were employed. Also, one's a vocal, one's instrumental. Now, the instrumental version, that 4-bar A section occurs 18 times. And in the Willie Nelson version, those 4 bars occur 5 times. The temporal granularity that we chose was 1 chord per beat. So basically, we looked at all the chord sequence information. It's aligned to something like 200 milliseconds or 100 milliseconds. So we basically decided to round everything to the nearest beat, and then take it from there. And then the tools that we used Chordino for chord transcription. We use Network X, which is a Python library for creating and processing the graph matrices and exporting them to Cytoscape, which is normally used for bioinformatics, and that's a association network and graph theory visualization and analysis tool. It's really good if you're looking for something. I recommend it. Now, I'm going to zip through these because there's quite a few slides, and basically they show the construction of a chord sequence graph. So you'll see the graph grow. Don't pay too much attention to the contents of the graph or the specifics. Just look at the way that it grows and take it from there. So this is the one that we looked at earlier, and you can see you've got, approximately the same size for the single events and the double events. We've got 5 sequences now. We're starting to see a more complex graph. These are all still from the instrumental jazz version. So these are all from the same performers doing it differently each time. 8 sequences, getting more complex, and you can start to see now that there's a definite backbone appearing through the middle. 12 sequences, and finally 18 sequences. So this is the graph that represents those 4 bars as they occur in the piece. So just take a look at that, and I'm going to walk through some observations that we were able to make from that. First of all, commonly reoccurring chords and transitions appear, and these indicate the essential chords of the sequence, which I like to refer to as the harmonic backbone. And this is an identifying sort of structure. And basically, these chords tend to be the ones that if you just played the chords to someone that knew the music or a jazz musician, that they would, when they heard the second chord, they would think, that sounds like it might be Georgia on my mind. They hear the third chord and they're like, yep, definitely Georgia on my mind. So this backbone that appears is essentially, it's not really a thumbprint because it's not unique, but it's the kind of thing that humans would recognize as being the fundamental underlying chord sequence or the changes for that particular tune. So the complexity of the graph indicates the complexity of the source material harmonically. So as you get more and more scattering in the graph, that will indicate that there's more variation at that point in the music with what the performers have been doing. Sorry, I think I've skipped a slide, pardon me. Shorter paths through the slide, going through the stronger arrows and blobs, indicate a very standard rendition of the material. So that's like bog standard, you buy a fake book or download a lead sheet off of the internet. Those are probably the changes that are going to be in there. But then if you were to look at the longer paths that go through the smaller arrows and the smaller nodes, those are the more unusual choices, and that's going to give you a more varied and a different sort of interpretation of the piece. Finally, the subgraph scattering, so the amount of activity sort of top to bottom, indicates the degree of harmonic variety at that point. So there's not a lot of scattering happening at this point of the A7 or the D minor 7. There's a bit of scattering between the A7 to the D7. Most of it's going directly from one chord to the next, but there are a few varieties. But when you get over here to the other half, you can see the sky's the limit, and that's where the musicians are really varying that to keep it interesting every time they play it. That slide I've just zipped over is just a concise listing if you want to look at the slides later of all the observations. The second example, we looked at a version by country singer Willie Nelson. Now, this material only appears 5 times in his recording. So that's the graph. I'm going to compare it now to 5 sequences from the instrumental version that we looked at before. And you can see, hopefully, that the instrumental version is a bit more complex, even after 5 instances. So the node count, well, actually, sorry, I've got my, pardon me, technical difficulty. Yes. So there's a reduced node count in the Willie Nelson version, which indicates that there's a reduced harmonic complexity to his version. The range of chords that he's used is more limited than in the jazz version. So the jazz players were basically using a larger jazz vocabulary. And there's less variation in the event. You can see more strong lines going through. Most of them tend to follow one path through, which means that most of the time when he did it, he was playing it the same way. However, even with that simple diagram, we can still see that the backbone is still there and it's still evident. Those are the observations that I've just talked over. And now quickly on to the third example. Basically, this was just combining the two previous graphs into one graph. So as you can see, it's even more complex, but it's there and there's a backbone. What do we find from this? Multiple versions of different recordings, different styles, different everything can still be combined into a single graph. It accommodates musical differences in the sources, such as tempo, key, style, chord choice, etc. Shared harmonic similarities between the two are evident. So we see the big orange blobs and the sort of lighter kind of orange blobs. Those are the things that were shared between the two. And notably, the ability of the graph to distill essential harmonic patterns appears to increase as the graph grows in scale. Right. Those are the observations that I've just talked over. Very quickly, a couple of slides on further work that needs to be done. There's still an amount of human pre-processing that needs to happen, mainly about sequence matching. You know, you've got a medley and there's 30 seconds in the middle of Georgia on My Mind. You know, we need to find that some way if we want to try and do a really good match. And that's a non-trivial question. So that's one of the things that we're looking at. Normalizing keys and aligning the time at the moment had to be done by humans, but we were planning on making some changes to the schema, which will make it, instead of focusing on specific chords, it will actually be focusing on harmonic events. So it will be describing each of those nodes or circles will be a functional chord rather than a chord name. Also, we plan to add a qualitative dimension that will indicate, it'll basically cluster the chords up and down by quality of sound to a human. So the similar sounding stuff will be grouped together and the more dissonant sounding stuff will be split apart. And that will make it expose a lot more information in terms of what a human would actually hear. Further work, we need to do some evaluation on it. So the next stage will be to formally evaluate the performance, to do a full implementation using a mixture of symbolic and audio information, and to try and develop some methods and metrics to measure the similarity of the sequences between the graphs. So you've got two graphs and you want to say, this one is really similar to that one, or those two are not the same at all. And that's really what we're headed for in terms of using this as a tool for discovery and recommendation. And also things like cover detection, it would be useful for that as well. That's it. Thanks very much. I've gone 1 minute and 49 seconds over time. I apologize. There's a little bit of reference material here, but there's a lot more information in the full paper, and there's some contact information. And thanks for your time. And if anyone has any questions, etc., I'd be really happy to try and answer them. Thank you.
Thank you. Is there anyone who has a question? Oh, okay, two people. David?
I guess thanks. Thanks firstly, yeah, for a really interesting visualization of chord sequences as much as other things. You kind of approached it in your last slide. This thing that, especially with guitar-led music, there isn't really a difference between a minor seventh and a sixth chord. You know, a G minor 7 and B flat 6 are basically the same chord. And I wonder if you could talk a little bit more about your thoughts on how to, because there's some really interesting complexity in that graph and some really boring complexity. The boring complexity being substitution chords. And I wonder if you could talk a little bit about your thoughts about next steps for how to, you know, make that a bit.
Yeah, sure. Yeah, that's excellent observation, of course. Yeah, basically, I want to try and use tonal interval vectors to create an actual coordinate in a sort of qualitative space for each one of the nodes. And so, because they're based on pitch classes, the B flat, B flat 6 and G minor 7 will basically be mapped to the same location. So that'll remove that problem, I think. So. I don't know if that's a really short, succinct answer to your question, but it's a really valid question. I mean, the other thing, of course, is, you could have two actually identical chords where the musicians are perceiving the same chord, but maybe a guitar string doesn't speak, or maybe the recording, there's a truck driving by, or someone hits a bass drum and a cymbal. And so the transcription tool identifies it as something different. For whatever reason, if there's no bass response, it could pick up a G dominant 7 as a B diminished triad. In a way, the design or the idea was to make it able to handle those differences rather than requiring everything to be cleaned up to be the same.
I mean, I guess that comes also to the question of whether the harmonic labels are the ones the musicians might have in mind. And of course, different musicians who are playing in a jazz group might have different ideas of what the harmony is, versus the ones that the hearer. Because the listener, as you say, might also not hear that bass that didn't quite sound, and so they might interpret the harmony. So yeah, I think something that's a bit less sort of strict in labeling might be really helpful.
Yeah, I mean, from my point of view, I thought about that, and I think actually, the performer's mind is a bit of a black hole, really. You don't really know what's going on in there. All we know is what's coming out of it. So I thought, there's no way we can answer the question of, did I think this was a B flat major 6 or G minor 7? It doesn't matter, really. Ultimately, we're just trying to find as long as it's kind of methodically described and clearly represented. I think that's, at least from my point of view, I think that's about as close as I can get to it. So yeah, it's definitely focused on what's hitting the listener rather than what was intended in the first place.
Great. So the next question is from Nestor.
Hi, very interesting presentation. Thank you.
Thank you.
I was actually going to touch on the same.
Before you start, can I just say thank you for all your help on helping me get my PDF ready for this. I just want to say that publicly. He's a complete star. Sorry, go ahead.
Thank you. And thank you for the great presentation. Very interesting. I was actually going to touch on the slide 34 issue about the different names for chords. In my experience, you already mentioned this, but I think pitch class sets will actually solve most of these issues. I was also thinking, because you're working with audio, so different spellings of the same chords, I'm thinking fully diminished 7th chords. You have maybe B fully diminished or G sharp fully diminished. How do you decide which one is it? And or simply just B flat or the A sharp, how you decide whether it's A sharp or B flat, major, minor, whatever. Yeah. So I think pitch class sets, in my experience, have helped to just cluster all of those into the same category. So, but I think you're aware of that already. And I was going to ask also, how do you decide the length of a chord sequence? Because I'm thinking if you just study one piece, it's basically one long chord sequence from start to end. So how do you cluster or separate into chunks of individual sequences? How you make that segmentation?
Okay, so I'll start with the second one first, if that's okay. So the answer is, from an autonomous point of view, I don't know yet. I mean, that's one of the big questions about this. At the moment, what we've done is, this is a kind of it's really defining the schema, showing that the schema works and that the schema in theory can scale. That's a big question, and so there was a slide a few slides previously where I was saying that we need to look at better methods of sequence searching, so that we can identify the kind of relevant portions of the thing. So what I'm kind of imagining is basically I wanted to try and make a kind of a dual of the graph, where it's another graph, but it's actually showing the nature of the transitions between one thing to the other rather than the details of the nodes. And then at that point, rather than being a big graph and comparing two graphs together, which is a really complex problem and very slow, it then becomes a sequence search. And so I'm hoping that by kind of summarizing the contents of the big graph in some way, I can reduce it down to a sequence search. So it'll be a faster search to basically zip through it and say, that looks like it's probably a possible match. So now let's dig into that again on another level and see whether those things actually match up. But at the moment, I mean, it's totally just me sitting down going, that's an introduction snip. I'm not looking at that right now. Okay, that's actually the tune. I'm looking at that. And then the first question, or the first point about the PC sets. Yeah, absolutely. I mean, when I started working on this, I wasn't really that familiar with PC sets, pitch class sets. And so then I looked at trying to implement it using pitch class sets. But the thing is with that, I feel like they're mathematically really useful, but humanly, I don't really think they're that useful to a person looking at this, trying to use it as a tool. And they don't really show functional progression. So there's a step beyond that where you can to do some Fourier transforms, as you probably know, on the pitch class sets. And if you do Fourier transforms on them, you can use some of the coefficient and phase information to basically define what the pitch class set sounds like in a lot of ways. And so that was the thing I was talking about using that to stick them into a point in space. So that it's actually the trajectory through this qualitative space that really defines how the sequence sounds. And that's actually what I'm interested in, is looking at the trajectory. The actual details of the nodes are kind of, they're a means to an end, at least, from my point of view. I think there might have been one other point, but I can't remember what it was. So I'll leave that. You can chase me up if I've forgotten anything.
Yeah, thank you.
Yeah, I have just one quick question or suggestion. So currently, the graph, each node, each chord is different from or similar to other chords equivalently, right? But actually, some chords are more similar to each other and more different from each other. Like, apple and pineapple are fruits. They are closer, but apple and desk are very different in this way. So I don't know the name of, I don't know how to measure the similarities between the chords. Probably there are so many theories that you can use. So eventually you want to use this graph for similarity comparison or cumbersome detection. Then probably having one more layer that reflect the similarities between chords might be helpful. How do you think about that?
Yeah, so that was the thing that we were just talking about taking these pitch class sets and doing this Fourier transform on them. And it basically what it would do is, if you have two chords that sound really similar, if you imagine a space, and that space is like how things sound, you can say, okay, well, a B flat major chord, it sounds, that spot over there represents what a B flat major chord sounds like. And then you've got a G minor chord. So it doesn't sound exactly the same, but it actually sounds pretty similar. So you can put it nearby in that space. And then if you rotate that space in a certain way, you might have a different minor chord, C sharp minor. And so in a different way, that actually sounds similar to the G minor chord because they're both minor chords. So if you look at it from a different angle, you can still see that they're close to each other. So by putting them into this space, it takes this graph, which I've got on the slide here. And if you look, there's this column of loads of things. Well, most of those sound really similar, and it will take the ones that sound similar and crush them together. And the ones that do sound different, if you've got some really crazy jazzer and they're doing like, I'm going to do some noise here, it'll stick that one further apart. So once that's happened, what I'm looking at is trying to find a way to define a trajectory through that map, that graph. And it's more about the general directions. So if I wanted to say, you want to get from Atlanta to New York, this is how you do it. I'm not going to tell you exactly which way to drive through my hometown in Virginia. I'm going to say, drive through my hometown in Virginia. And it doesn't matter if you go on the interstate or if you go on Highway 11. I mean, they're close enough that effectively it's the same trajectory. So that's the sort of, that's the solution to, I have considered that. And that's how we're tackling that.
Thank you.
Yeah, thank you.
So thank you so much for your presentation.
Thank you.
Yeah, in discussion.
Oh, can I just say very quickly before going, if anybody wants to get in touch with me, please feel free. And I'm really interested in hearing from anyone else that's working on anything similar, or if anyone's interested in doing any collaboration, please let me know, because I'm very much up for that. So thanks for the opportunity to present and all your help.
So, yeah, we have 2 more presentation sessions after a break. I hope you enjoy them.
Yes, and just a reminder to everyone, if you want to use the gather space, you're welcome to as a way of having post-talk social conversations or follow-up conversations with other people. So we'll see you at UTC 14:15 for our next session. So have a nice breakfast, lunch, or dinner, depending on where you are. Bye-bye.